Hi, so given the molecule SeO3, which happens to be selenium trioxide, first I'm going to draw the Lewis dot structure. And to do that, first I got to get the valence electrons. So for selenium, there's going to be 6 valence electrons. And then for oxygen, it's also 6. However, it's going to be multiplied by 3 because there's 3 in the molecule. So that's going to equal to 24 valence electrons. So now that we have that, I'm going to start with selenium in the middle, and then I'm going to branch off the oxygens. However, being that the selenium in the middle is only left with 6, it's not going to fill our octet rule. Therefore, in order to do that, to fill the octet rule and also have oxygen have fill the octet rule too, I'm going to do a double bond right here. So that's my finished Lewis dot structure. As for the resonance structures, it's going to be similar, just moving the double bond around. So there are my 3 Lewis dot structures with the resonance structures. As for the formal charge, I'm using the equation, I guess, which is the valence electrons minus the non-bonding electrons, and then that's subtracted by the bonding ones divided by 2. So for selenium, starting with selenium, there's 6 valence electrons and there are 0 non-bonding electrons. And then there's the bonding electrons divided by 2 would be 4. Therefore, the formal charge for selenium is going to be a +2 charge. As for the first oxygen, it's going to be 6 valence electrons, and there are actually 6 non-bonding electrons, subtracted by the bonding electrons divided by 2, which would be 1. So therefore, that would mean that oxygen would have a -1 charge. As for the last oxygen, the double bonded one, it's going to be a little different. Well, it's going to be different. 6 valence electrons, and then there's going to be 4 non-bonding electrons, and then the bonding electrons divided by 2 is 2, and that's going to equal to 0 formal charge. So there's my math I did for the formal charges. The one on the bottom, so this is the formal charge, or not the double bonded one, and these are the same for the other 2 oxygens. And actually, I'm gonna write in the formal charges just to be sure that we know where they go. Okay, and if you look right here, I wrote in the formal charges just in all resonance structures. I just wrote them right here so you can see them all where they go. they're the same. They just shift over. So for number 4, I'm determining my molecular geometry. And it's going to be the same shape for all of them. So I'm just going to do one of them. So it's going to be a trigonal planar. So selenium is going to be in the middle. So for our there's my molecular geometry. It's a trigonal planar, and the bond angles are going to be all 120 degrees. So for number 5, what I'm going to do is show all polar covalent bonds using delta notation. So the way I determined the delta notation was using the trend for the electronegativity for these elements. So very quickly, I'm going to draw a Lewis dot structure for this example. So being that oxygen is more electronegative than selenium, this means that when we look at it, the delta notation is going to be going outwards. So it's going to go out. It's going to go out. Okay, so here's my delta notation. So since selenium is less electronegative than oxygen, the delta notation is going to start at selenium and it's going to go outwards. So for all of the oxygens, the delta notation is going outwards. So it's going outwards every direction. For the last one, for number 6, I have to determine if the molecule is not as polar or non-polar, and I determined that it was non-polar because it has even oxygens pulling outwards, so they're pulling outwards, so that makes it non-polar. It has even pull, so if it has even pull, then that determines that it's non-polar.